Today is part B of week 4's lesson, and we're going to be describing electrostatic force using arrow math. So today you're going to get your equation for Coulomb's law and take some notes on that, and we'll do one warm-up at the end. So a quick review from what we talked about yesterday. This is a hydrogen atom model and it has electrons on the outside and protons in the center in the nucleus of the atom. And it's these charges that we're going to be talking about, negative and positive charges. And the big picture from yesterday was to remember that opposite charges attract. So you have a negative and positive, they're going to attract towards each other. And then the like charges repel. So if you have two negatives, they push away. Two positives, they push away. If I were to have a sphere of negative charges and a sphere of positive charges hanging from strings like this, and I put them kind of close together, what would happen to these two spheres? So if you remember, opposite charges attract, and these are opposite charges, they're plus and minus. So what will happen is they will be pulled together like this. Their forces, the electrostatic force will be pulled together like that. What do you suppose will happen to these two spheres? One is negative and the other one is negative as well. Remember that like charges repel. They repel, which means they push away. So they will go something like this. And their forces will be pushing away from each other. So this was electrostatic force. It works for all atoms because the protons are in the middle of all atoms and they have electrons on the outside. They may have different numbers of those. And this is very similar to something else we talked about earlier this month, and that is gravitational force. Here we have the Earth and the Moon, and they pull together as well. So electrostatic force and gravitational force are very similar. As a matter of fact, they're going to have very similar equations. Okay, for gravitational force, if you remember the force of gravity, we had the masses of the two objects on top. More mass of the Earth or more mass of the Moon means more force of gravity. And then we had the distances on the bottom. The distance is important too. More distance meant less force of gravity. That's why distance is on the bottom. Actually, it's distance squared. Over here, for electrostatic force, we have almost, you can look at these equations, they're very similar. For electrostatic force, we still have the distance. So the distance is the exact same thing. The distance, the farther away, the less the force will be, just like in gravity. And then we have, up here we have Q1 and Q2, where over here we had M1 and M2. So these M's were for mass, because the mass of the two objects was important. These Q's, again, it's a weird letter to use, Q, but you know, they're running out of letters. So the Q actually stands for charge, the amount of charge on these. Think of it as the number of electrons or the number of protons. And so we know, just like mass, more charge is more force. That's why the charge is on top. And finally, we have this. This is big G, which is always constant. It's the constant of the universe, and it's the same number for everything in the universe. Well, this isn't also a constant. It's the electric constant, electrostatic constant. It is always constant as well. So notice how these equations are very similar. Electrostatic force, force of gravity, constants. Instead of masses on top, we have squares still on the bottom. What we're going to do now is we're just going to take notes on this and then do a warm-up. So get out notes unit 6.5. Notice this is not 6.4. We're going right to 6.5. So they look something like this. So go ahead and glue in these notes to your notebook, and then we will fill in these notes. So here's our equation, electrostatic force, and like I said, there's the Coulomb's constant, Ke. Q1 is charge of object 1, and Q2 is charge of object 2. And then the distance between them squared. We do measure charge in C's right here. We measure charge in coulombs. Anything that's charged has a number of coulombs of charge. Anything else named after the guy who came up with the law, Coulomb's law. Let's go ahead and draw our picture and label it. It's going to be very similar to the picture for gravity. It goes right next to the equation. You have two objects. It can be any two objects. And this will be Q1 in coulombs and Q2 also in coulombs, and then the distance between them. Remember, it's the distance between their centers, not the distance between the edges, the distance between the centers in meters. That's why that little plus doesn't mean charge. That little plus means center, the center of each object. The charge can be positive or negative. Both charges can be positive, both of them can be negative, or one can be positive and the other one can be negative. So go ahead and write this down in your picture. You have the two charges, Q1 and Q2, you have the distance between them, and they go with the equation. Again, all this can be found in your big equation sheet, the yellow paper in the front of your notebook. Here's the gravitational force. Here's the electrostatic force. They're written right next to each other, so you can compare them and see how similar they are. Then down here, I do have the charge of an electron. An electron is 1.6 times 10 to the minus 19 coulombs. That means you move the decimal point over 19 times to the left. It's a very small charge on one electron, of course. Then you got Coulomb's constant, Ke, and then you have gravitational constant, big G, down here. I do want you to notice this right here. This Coulomb's constant is times 10 to the 9th, whereas gravitational constant is times 10 to the minus 11th. Okay, so what does that mean? That means that we are going to be moving the decimal here 9 places to the right to make it bigger by 9. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So it'll be like 9 with 9 zeros. So the constant is going to be 9 with 9 zeros. 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the constant for the electrostatic force. Okay, but whereas for the gravitational constant is 10 to the minus 11, so it goes the other way, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and that's the decimal right there. So that will be more like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 6, 7. Okay. Notice the difference in these two constants. Gravitational constant is much smaller than electrostatic constant because the gravitational force overall is much weaker. You need a lot of mass in order to measure the gravitational force, whereas you only need a little bit of charge to measure the electrostatic force. So the last part of our notes is just comparing gravity to electricity. Electric force is much stronger, so we know that because Ke equals 10 to the what and G equals 10 to the what. Get these off of your yellow paper. What goes here? Right, it's 10 to the 9th. 10 to the 9th. Ke equals 10 to the 9th. That's why it's such a big number. Now what about big G, 10 to the what? 10 to the minus 11. Remember, it was a very small number, right? Those are the numbers we have, 10 to the 9th and 10 to the minus 11. So you can see that electric force is much stronger. And then the other difference between force of gravity and electrostatic force is how they repel and attract. Gravity can only pull things together. That's the only thing gravity can do. But electrostatic force can push or pull. For example, if you have two positive charges, you're going to get a positive force, which means they're pushing away from each other. But if you get a positive and a minus charge, when you put in the equation, you're going to get a negative. Positive times negative gives you negative. That means a pulling force, pulling together. So electric force can push or pull, but gravity can only pull. So go ahead and finish up your notes by copying this down. All right, we're going to finish up today with a warm-up, warm-up 3. This is, again, very similar to what we did with gravitational force, so I'm just going to jump right into this warm-up, but now it's going to be talking about charges instead of mass. Warm-up 3. What would happen to the force on each electron in this atom if 2 more protons are added? So see, notice how we have 1, 2, 3, 4 protons right here, but over here we got 1, 2, 3, 4, 5, 6 protons. So we added 2 protons to the middle, same electrons in the same orbitals. So the question is, what happens to the force of attraction or repulsion? What happens to electrostatic force if we add 2 protons to the middle? So claim. Remember, you guys are copying the blue, right? Copy the blue. So the claim, the electrostatic force on each electron would, we'll get back to this. Then evidence, the positive charge is what, while the distance is what? So going from this picture on the left to the picture on the right, what is happening to the positive charge? Right, it's increasing because it goes from 4 plus 4, it goes to plus 6. So it's increasing. What's happening to the distance between the charges, between the positive and negatives here and the positive and negatives here? What's happening to the distance when we go from the first picture to the second picture? Staying constant, because it's the same picture. Basically, the electrons are in the same orbital, so they have the same distance away as they did over here. Now we're going to put this in reasoning. We can see by Coulomb's law that, now we're just going to go through Coulomb's law. Here's Coulomb's law. So before we put the words in, we just got to do the arrows. First, Ke. What arrow goes above Ke? right? That's constant, right? That's why it's K for constant. It's always constant. Now what about for the distance? What's happening when we go from the first picture to the second picture? What is happening to the distance? It's staying constant. So we put constant arrow above distance. Now Q1 and Q2, we'll say Q1 is the charge of the electron. So looking at our two pictures, how's the charge of, and we're just talking about one single electron. So we're talking about the attraction between this electron and those protons, okay? So, or this electron and those protons. And so they're always going to be one electron in our comparison. So that's going to be constant because it's going to be one electron. In any one of the cases, we're going to pick one as one electron. Now, charge 2 is going to be the charge that the electron is attracted to. So it's going to be the total charge that is being attracted to. So what happens to the charge in the middle? It's increasing. We said the charge is increasing because there's more protons in the middle, so the charge is increasing. Now, we just got to do arrow math. Look at this. Everything's constant except for the right. On the right, the charge is increasing, so they're both equal. So what has to happen to the electrostatic force? It also has to increase, right? If the right side gets bigger, the left side has to get bigger. So now we can fill in the words for our reasoning, okay? We can see by Coulomb's law that increasing one of the charges, right? We're increasing this charge while keeping the other charge. What are we doing to the other charge? It's constant, right? Staying constant. And distance, what's happening to distance? Staying constant. Will cause the force to do what? So what's the force doing? The electrostatic force is increasing. So now we have our answer. Electrostatic force on each electron would do what? Increase. So go ahead. This is warm-up 3. Go right on down here and write your claim, evidence, and reasoning, and don't forget your equation with the arrow math.